What's up, everybody? I'm Steve, and today we're doing USACO 2024 US Open Contest at the bronze level, problem number 1, logical moves. Farmer John has a Boolean statement that is n keywords long, between 1 and 2 times 10 to the 5th, with n being an odd number. Only true or false appear in odd positions. So positions 1, 3, 5 could be true, false, true. Only and or appear in even positions. So 2 and 4 is going to be like an and or an or. A phrase of the form x operator y, where x and y are either true or false, and operators an and or an or evaluates as follows. X and y evaluates true if both x and y are true and false otherwise. X or y evaluates true if either x or y is true and false otherwise. So this is the same as any Boolean expression that you'll have in computer science. If you have true and true, you've got true. But if there's anything in a sequence of ands that's false, the whole statement is false, because they all have to be true. With or, only one of them has to be true for the whole statement to be true. And that's going to be the key to how we solve this problem. When evaluating this statement, FJ has to take order of precedence in Moo language into account, similarly to C++, and takes priority over or. More specifically, to evaluate the statement, repeat the following step until the statement consists of only one keyword. Number 1, if the statement contains an and, choose any of them and replace the phrase surrounding it with its evaluation. I had to read this one twice. What they're saying is to choose any statement containing an and to evaluate it. A and B or C and D. I can do either this and first or this and first. You can do them in any order you want. Otherwise, the statement contains an or. Choose any of them and replace the phrase surrounding it with its evaluation. This whole, for example, statement down here contains an or. You can choose any or statement and replace it with the evaluation, but only when there are no ands left. So what's going to happen is I might have A and B or C and D or E and F. So I'll do the ands first. We'll evaluate A and B, and that's going to be either true or false. We'll evaluate C and D, and that's going to be either true or false. We'll evaluate E and F, and that's going to be either true or false. Then for the or statements, which I have 2 of them, one here and one here, I can pick either one and evaluate it. So true or F is going to become true, and then true or true is going to become true, and the whole statement evaluates true. It may be proven that if multiple phrases can be evaluated during a given step, it does not matter which one is chosen. The statement will always evaluate to the same value. Because of the nature of and, everything has to be true. So if I have A and B and C and D, if any one of them is false, the whole thing's false, which means I can evaluate them in any order. Farmer John has Q, where Q is between 1 and 2 times 10 to the 5th queries. This is a big problem because we can see that the n keywords is up to 2 times 10 to the 5th, and the number of queries is up to 2 times 10 to the 5th. So that's setting us up for a situation where, like an n squared algorithm, or in this case n times q, is going to go over time complexity and timeout. Like a lot of these problems, we're going to have to do some sort of a pre-processing and figure out how to solve these either in logarithmic time, using some sort of a binary search, or in constant time. There's a lot of problems that have this sort of idea. Walking around the fence has a similar one. As you're solving the problem, you're keeping track of what you've seen, so that later, to go from here to here, you don't have to walk through it. You can just see what happened here, and find the difference. In each query, he gives you 2 integers, L and R. And this is a left and a right, clearly. One is less than or equal to L and R, which is less than or equal to N. It's important to kind of read these out. L and R can be as low as 1, can be as high as N, and they're allowed to be equal to 1, equal to N, and equal to each other. So it's possible that L and R are both 5, for example, or that they're both 1, or that it's 1 to N, or that they're both N, or anything in between. Also, it says L and R are both odd. Only true or false appear in the odd positions. The left and right are going to identify Booleans. So you're going to have something like true and false or false. That left to right is going to designate some subset of this. It gives you the 2 integers and deletes the segment from keyword L to keyword R inclusive. In turn, he wishes to replace the segment he just deleted with just one simple true or false, so that the whole statement evaluates to a certain Boolean value. Help FJ determine if this is possible. This one's tricky. Let's go ahead and look at the sample input. First simplification, I don't like working with words. False and true or true. I would process this and just keep the first letter of each word. And I would put it in a character array rather than having it be space separated. If I've got false and true or true, my n is 5. 1, 2, 3, 4, 5. I'm going to do F-A-T-O-T. And then with a single character evaluation, I can determine whether something is a false, a true, an and, or an or. You could also do these symbolically. You could turn them into integers. You could turn them into symbols, like I could use the ampersand. But I feel like it's simple just to take the first letter of every word. I'm just going to load the words one at a time, pull the first letter out, and stick that into some sort of a collection. So I'm going to be given subsets. You can see here's 1 to 1, 1 to 3, 1 to 5, 3 to 3, 3 to 3, 5 to 5, 5 to 5. And they're going to tell me that they want to replace things in that range with something, my choice, either true or false, such that the entire expression evaluates as what is requested here. false or true. Just as an example, let's grab one out of the middle. We want to replace from 1 to 3, which is here, false and true. I want the whole expression to evaluate as true after I've replaced this with something. If I want it to evaluate as true, I don't have any not anywhere in here. True and true, true or true, both will evaluate as true. So if my goal is to make it evaluate as true, I should just always choose true. And if I want it to be false, I should always choose false. The absence of a not means that there's never going to be a situation where you're going to get a true by replacing a section with a false, because we're not going to have any way to invert. Now, the problem is, how do we then, in constant time, evaluate whether or not this entire expression is going to end up being true or false after this replacement has occurred? Because remember, we are not allowed to then scan through the whole thing and evaluate it. So what we need to do is we need to start picking apart these expressions and to try to figure out how can we make a bookkeeping that will allow us to go to index 1 and go to index 3 and find out what's outside of this range. Let's look at the next page. Okay, that one's a little longer. So let's do the one that has 3 to 11. We're going to do 1, 2, 3, 4, 9, 10, 11, 12, 13. False or true and false. The two of them that I really want to look at are these 3 to 11s. It says deleting from 3 to 11, which is going to be here to here. It is not possible to make that become true, but it is possible to make that become false. So let's see if we can figure out why that is. I've got 2 questions to ask myself. If I want this whole entire statement to become true, and I'm replacing this with a true, why is it that I can't make this whole thing become true? This no means it's impossible for it to be true. This whole section, if I were to replace this with a true, what I'm left with is false or true and false. The problem is that this ended up in a situation where I have true and false can't be true, and then I have false or that. And there's nothing I can make this that's going to cause something and false to become true. That's the first major hint on this. We need to know how these break down so that when we have index 3 here and index 11 here, we need to have something here and something here, probably another sort of data structure that's storing some sort of information so that I know that here is part of a statement that includes an and false, and that to the left of me here, there are no trues. We're going to switch to a visualization to kind of see how this breaks down, because while this is great drawing, I want to get something colorful and something visual in front of me. Without further ado, that's the problem, and I will see you in the visualization section. All right, so we're trying to figure out how to visualize this one. One thing that's going to make this a little bit easier is just simplifying the way the visualization looks. What I'm going to do is I'm going to use these chips. The green one is going to be a true, red one's going to be a false. Those are going to be in odd numbered positions. For and, I'm just going to do a plus symbol. And for or, I'm just going to do a vertical line. True and true or false. Let's go ahead and do a couple more. We'll have another and. So I've got 5 and 7, or false, or false and false. This is still really hard to visualize. What we need to do is we kind of need to figure out how to put these into groups. Any and group is important because an and group means that all the members of that are together. 1 and 3, this has to all be true for this to be true. But an or is kind of a separating thing. So if I have these guys over here, or 5 and 7, or, let's go ahead and just remove all the ors. Now we don't have to do this from programming, just for the sake of our visualization, because these are distinct groups. And the or doesn't really contribute anything other than clutter. What we really have here is 1, 2, 3, 4. We have 5 groups. These 5 groups, each one of them is true only if all of them are true. Let's go ahead and put a chip under them to say if they're all true. 1 and 3, this is all true. 5 and 7, that's a false. 9 is by itself, that's a false. 11 is by itself, that's a true. 13 and 15 are going to be a false. I've now kind of simplified these, because now what I can see is I can see where my trues are and I can see where my falses are. Because of the way that ors work, this whole thing is true if any one single of these groups is a true. If I were to replace some section here, if this 11 still exists, the whole statement is true. Because if this is or, true, or anything, if we want it to be true, we've succeeded. And if we want it to be false, there's nothing we can do. There's nothing you can replace this subsection with or this subsection with that will cause the whole statement to become false because of the fact we've got this true here. If I want the whole thing to be false, I have to break up this group here and make this group false as well as this group here, which means I need to at least be from 3 to 11. If I replaced from 3 to 11 with a false, I'd have true and false, which would be false. And then I'd have false over here. And if I have false or false, then I've got false. Let's try to simplify this a little bit further. I want to pull out all of the numbers entirely and just have these as groups. So here's true and true. false and true, false by itself, here's a true by itself, and here's false and false. And these are still numbered. In fact, let me see if I can write on these. This is 1, 3, 5. I don't think red's going to show up. I got my green mark for this. 7, 9, 11, and then we'll go 5. Can I make this work? I bet that'll show up as black. Yeah, it shows up as black. Sweet. I love how colors work. 7, 9, 11, 13, and 15. And right now, I'm just trying to simplify this as much as possible. True and true, false and true, false by itself, true by itself, false and false. In order to have this be true, if this is present or this is present, the whole thing is true no matter what. I don't need to do much to make this true. But if I want to make it false, I have to make the 11 group here become a false. I have to make it so that at least 1 in this group becomes false. So if I were to place from 3 to 11, or from 1 to 11, or from 3 or 1 to 13 or 15. Any one of those replacements would potentially break both of these groups up. They're going to give you a subsection. They're going to say, for example, you can replace from 5 to 11. What I need to know in constant time is, are there any groups to the left of the 5 or to the right of the 11 where everything is true in a group? For example, 1 and 3. Everything is true in this group. So if I'm replacing from 5 to 11, no matter what I replace that with, because there is a group to the left of me that has all trues in it, I can't possibly make this expression become false. Likewise, if I go 3 to 9, then to the left of the 3, there's not a complete group where everything is true, but to the right of the 9, there is a complete group where everything is true. A really simple way to do that would just be to start walking through and figure out for each one of these numbers, how many complete groups are there to the left of it where everything is true. So for example, from here is 0, because there's no complete groups to the left of that one, and there's no complete groups to the left of this one either. But once I get to the 5, I can add 1 to my counter of how many all true groups I've seen, and now I've got 1. 1, 1, 1, still 1. But having now completed that group and realizing that it has all trues, I'm up to 2 and 2. When I do a replacement, if I'm replacing with a starting position that has any number that's not 0, for example, starting from 5, starting from 7, starting from 9, starting from 11, 13, or 15, I know that to the left of me, there's a group that's all true, which means that if my position is 5 for starting, I cannot possibly make this statement false. It's true no matter what, because there is one group to the left of me where everything is true. But what if my starting position is 3? Then I still have this 11 to account for. So I got to go the other way. So as of here, there are 0. As of here, there are 0. As of here, there's technically 0 to the right of it. But once I get to here, there is one group to the right of this, where everything is true. And that's this 11 right here. Still 1, 1, 1, 1. So now let's look at what we have. If my replacement range is from 1 to 9, from my starting group, I see that there's 0 all true groups to the left of me. But from my 9, I can see there's 1 all true group to the right of me, which means any replacement from 1 to 9 can only yield true, which means if we're asked to produce false, the answer is no. And we're asked to produce true, the answer is yes. If I'm replacing any subset where to the left of me there's an all true group, or to the right of me there's an all true group, I can only make true. Let's go ahead and make this 2 groups. 1 and 3 and 5 and 7, and then 9 and 11 and 13 and 15. And I'm gonna go ahead and swap that 15 out for a true 15. What's gonna happen if I wanted to replace from 5 to 13? And I can see that if this is 1 and 3 and true and 15, then I've got true and true and true and true. I can see that if I replace all of my falses here with true, then I can still make it all true. Likewise, from 9 to 13. If I were to replace 9 to 13, this is false and true and false and true. If I replace this with true so that I have true and true, then I've made a group where everything is true, which means it'll evaluate true. Or I can leave it as false if I want it to evaluate as false. So this is a little trickier. The first pass evaluation is, do I have a complete group to my left or a complete group to my right where everything is true? And if that's the case, then I don't have to get into this level of granularity. But if all of those are zeros, so I have no groups to the left that are all true, no groups to the right are all true, I need something a little more clever. If I replace, for example, starting from 5 and ending at 5, and I have a subset here, how many falses were to the left of the 5 and how many falses were to the right of the 5? Let's go ahead and do this counting falses from left to right. So as of here, 0 falses to my left, still 0 falses to my left, still 0 falses to my left, and now finally 1 false to my left. Going the other way. If I were to replace in this section from 5 to 5, I can see I have 0 falses to the right and 0 falses to the left, which means if I replace this, then I know that there's no falses left. From here to here, I see that there's 0 falses to the left. I see there's 0 falses to the right. So a 3 to 5 replacement would let me replace all the falses. Anytime I start and end on a 0, that means that the segment I'm replacing doesn't have any falses outside of it. And that would mean that all the falses are inside of it if there are any. Let's look at one where that's not the case. Let's say we're going to do a 1 to 3 replacement. To the left, I have 0 falses, but to the right, I have 1 false. If there are any falses left in the statement is false. I can see that I've got a false to my right, which means this is just going to be false. I've already checked, and I know that there's no all true groups to my left, and there's no all true groups to my right, and this subsection is containing a false. That means that the whole entire expression is false, because nothing to my left is true, nothing to my right is true, and this subsection, the 1 to 3 subsection, doesn't contain all the falses, because there's a false to the right of it. Let's look at a larger one. Let's say like this is all in one big expression from here. Left to right, how many falses are there? 1 as of here, still 1, becomes 2, still 2, and then becomes 3. I don't have any 3s yet. 3. Right to left, how many falses are there to the right of me? 0 falses to the right, 0 falses to the right, 1, 1, 2 to the right, and now 3 and 3. If I were to replace from 5 to 9, from 5, I can see there's 0 falses to the left, but from 9, I can see that there's 1 false to the right, which means I can't make this statement become true because there's going to be a false left. From 5 to 11, 0 falses to the left, 1 false to the right. 7 to 11 has 1 false to the left, 1 false to the right. 7 to 13 has 1 false to the left, 0 falses to the right. Only here, from 5 to 13, will we have 0 falses to the left and 0 falses to the right, which means that if I have no falses to the left and no falses to the right and I replace this, I can make this true if I want, or I can make this false as I want. So that's it for the visualization. Let's write the code. So before we get started on the code, just briefly, I want to run over the pseudocode, and this will be shared the same procedure between C++, Java, and Python. The first thing I want to do, load the data and simplify. By simplify, I'm going to take false and true or true as input. And I'm going to just turn that to FATOT. We're going to put that in some sort of a structure. Maybe I'll do like an array of characters. But I just need the first letter of each one. I don't need the whole word. Probably call it something like expression. So I'm going to make 4 arrays of numbers. It'll be called left all true, which is how many all true and sequences are there to the left of it. It's always going to be starting on an odd number and ending on an odd number. I'm going to go ahead and fill it in for the even numbers just because that makes it easy. So we'll have 0, 0, 0, 0, 0. We're going to have right all true. It's going to be the same thing. For each subsection, left false count, which is going to be within any subsection of trues and falses where it's all ands, how many to the left of it are going to be false. So again, starting as all zeros. And then right false count. I'm going to set these arrays up. Then I'm going to go left to right. As I'm going left to right, I'm going to be keeping track of how many subsections are all true. If I have like true and true or, at the moment I hit that or, I'm going to raise that count to 1. And then from then on, my count is going to be 1. If I hit another true or, where it's only trues and then an or, that count will raise to 2. Then at any given index, you'll know how many entire sequences of something and something there are where everything is true. So then when I'm going to cut from here to here, if I know before here there's something where it's all true and then an or, then I know that there's no way to make it false. We're going to have a count of how many complete groups there are. All true is going to start at 0. We're going to have false count is going to start at 0. So I'm going to iterate through left to right. As I go left to right, here I've got false and at that point, left false count becomes 1 because there's 1 false to the left of that in that and expression. Here's true. Left false count is still 1. I hit or, that's going to reset this from 1 back to 0 because that's now a different expression. And then true, that's by itself, no falses to the left of that. That's my left to right pass. Then my right to left pass is going to happen. So here I have true or, and at that moment, I'm going to raise my all true counter to 1. We're going to treat each something and something and something as a group. So I've got one group to the right where everything is true. That's just this single true by itself. That's going to remain a 1 all the way throughout. 1, 1, 1 in this case. Once I've done left to right and then right to left, I then am going to write the code that will read in these expressions one by one. And using the indexes, for example, 1 to 3, I'll look at index 1 and I'll say, okay, from 1 to 3, how many all true are there to the left? There's none. To 3, how many all true are there to the right? There's 1. There's one expression where everything is true to the right of this, and that's this or true right here, which means the expression can only possibly be true. If we have a subsection, for example, is 1 to 1, if I know that to the right there are no falses, and to the left there are no falses, then that means that this expression can be made true by changing it to true. But if I wanted to change from 3 to 3, I can see to the right there are no falses, but to the left, this expression, false and true, has 1 false. We'll test that a little bit as we go, and it'll make sense as we go. I'll try to do a little testing on each of them. And that's it for the pseudocode. I just want to kind of generally explain. We're going to make 1 pass to the left, 1 pass to the right, and then we're going to analyze. Close that. and q. I want to double check my variables right. We're going to cn, n, and q for int I equals 1 while I is less than or equal to n, I plus plus. We're going to have char, let's call it expression, n plus 1, so I can one index, int left true intervals, n plus 1, right true interval, n plus 1, left false count, n plus 1, right false count, n plus 1. Go ahead and do string temp. So then we'll do cn temp. This is going to be the false and true or true. I'm going to record just the first letter into the expression. Expression I equals temp at first character. At the same time, since this is C++, these don't initialize to 0, so we're going to do left true int at I equals 0 and do the same for all the other ones. I'm going to make my first initial pass where I'm going to count up how many all true intervals I have, as well as how many falses I have. Now, these will jive really well together because if I know how many falses there are and I hit an OR and there's 0 falses, then I know that that entire interval is true. Int true intervals is going to be 0. Int false count is going to be 0. For I equals 1 while I is less than or equal to, less than or equal to n, I plus plus. Left true interval at I equals true intervals. Left false count at I is going to be false count. If expression at I is equal to an F, then false count plus plus. Else if expression equals O for OR, if it's a false, I add 1 to my false count because then as far as the next item is concerned, there's a false to its left. If I hit an OR, then if my false count is 0, then I've hit an OR of an expression where there's no falses in it. And if there's no falses in it, then that means that this is an entire interval where everything is true because I made it all the way to an OR and I didn't hit any falses. And since the first item has to be either true or false, by the time I get to an OR, I'll have at least one item that's either true or false. And then either way, once I hit an OR, I have to set false count back to 0. So if it was 0, that's great. If it wasn't 0, it goes back to 0. And that should be it for passing from left to right. For right to left, it's pretty much the exact same thing. I'm just going to copy paste because no reason why not. I equals n, while I is greater than or equal to 1, I minus minus. Then this is going to become right true interval instead of left true interval. Right true interval equals true intervals. Oh, we're going to have to reset true intervals back to 0. False count also has to be reset back to 0. Because I'll end on either a true or a false. If I end on a false, my false count would be 1. But if there's a false at the very end, then that can't be to the left of anything if it's the last item. So resetting the false count back to 0 without recording it doesn't really matter. So I got right true intervals and then right false count. Right false count. True intervals and false count. Let's see then. False count. I don't think anything else changes. The false count expression. Yep. Okay, that's it. This is a good time for sanity check. We're kind of blowing through this pretty fast. So let's take a moment for int I equals 1 while I is less than or equal to n, I plus plus. What I want to do is see out my I value. Left true interval at I. Left false count at I. Right false count at I. Right true interval at I. Let's actually even also print out the expression. Expression I. And this will just be a way we can kind of double check and make sure that our initial calculation is good. But we need something larger than false and true or true. All right, I grabbed the test case from the visualization. What we have here is true and true, both true, or false and true, or false by itself, or true by itself, or false and false. And as a subset, I just made up 3 to 9. Actually, we should do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 would be interesting. 3, 11 false, and then let's do 3, 9 true, 3, 9 true, 3, 11 true. That'd be 4 of them. For right now, though, we're just going to test this part because I haven't even written any code past that yet. We'll save that. I'm going to make logical. Ooh, what do we do? Else if expression, oh, okay, right. Expression at I, oh, intervals, I spelled that wrong. For intervals, and then here, make, okay, great. Do logical, feed it our input. Oh, let's do, just for fun, if I is less than 10, see out an extra space. Paste. All right, so I have left true interval, left false count. We can't look at the right stuff yet. So for right now, we can ignore the last 2 columns. So I have true and true, or, And at that moment, that's when our left true interval should go up to 1. We're not going to see that until here, though. But that's okay, because we're never going to do a cut from an OR. So starting from this false, we now know that to the left of this false, there is a complete interval, 0 to many ands, where everything is true. What that 1 indicates is if this is the left side of any cut, you could never make this false because there's already an interval to the left of it. And because of this OR, the whole expression is going to be true no matter what. And from there, the actual count doesn't really matter. So it gets up to 2 here. The fact that this is 2 doesn't really mean anything for this exact problem. If we had a version that had parentheses, it might be important. Ultimately, as long as this is greater than 0, that means that the expression, if this is the left side of a cut, can never be true. First time we encountered a false is right here, which means that from this and, there is a false to the left of it. There's a true, there's a false to the left of it. What that means is that if we cut here, we can't make this particular expression true because there's a false to the left. So if this is the left side of a cut, and then the right side is down here somewhere, this particular sub-expression cannot be made to be true because there's already a false here. When we hit the OR, it resets our false count back down to 0. But here's a false, so it goes back up to 1. And again with this one, false OR, we're back to 0 again because it's a different expression. Here's a false and false. As of this false, there is at least 1 false to the left of it. If we cut this starting from here and cut to the right, for example, if we cut 15 to 15, I can't make this last expression become true because there is a false to the left of it. And then likewise, because of the fact there are 2 entire expressions that are all true. One of them is this true and true at the beginning. One is this or true or right here in the middle. Then either way, if the starting point is past that, we can't make it false. Same thing now from right to left. We go right to left. Here's false. And then now our false count is up to 1. False again. False count is 2. That's an OR. So we're back down to false count of 0. There's that true or true, which means now I have a 1 here, which means to the right of this point, there is a true by itself in an expression, or a true and true. Everything's true, which means if the right side cuts to here, we can't make that false because there's already a true to the right of it. This all looks good. And we'll start reading the individual queries. For int I equals 0, I is less than q, I plus plus. Start, end, and then cn start, end, string goal, I suppose. That's what we want. We'll just compare to goal 0. If goal 0 is f, that means our goal is to make this statement be false. Else, we won't error check. We'll just do else. If the goal is not f, then it must be t, so it's true. Those are the 2 situations. We're either trying to make it true or we're trying to make it false. If we're trying to make it false, then if left true intervals at the starting point is greater than 0, or the right true intervals at the ending point is greater than 0, then that means that we're cutting something where there's either an all true interval to the left or an all true interval to the right. Or I guess if you're facing me, it's that way. We have an all true to the outside on one of the 2 sides. If we have an all true interval to one of the 2 sides and we're trying to make it false, there's nothing we can do. Then we've failed. Cout n. Otherwise, we succeed by default. Because if our goal is to make it false and there's no all true intervals to the outside, then whatever interval we're in, we can just make that expression false. Because no matter how large or small that is or what else is on the inside of it, if I make that subsection false, even if it's true and false and true, whole thing's false. Else cout y. Now, if we're trying to make it true, that's a little trickier. If left true interval at start is greater than 0, or right true interval at end is greater than 0, then we've succeeded by default because there's an all true interval outside, which means we're good. We've got it. If there are no intervals to the outside where everything is true already, we have to make this interval true. If we have to make this interval true, the only way to do it is there can't be any falses to the left of the part of the interval we're in, or any falses to the right of the part of the interval we're in. As long as there's no falses to the left and no falses to the right, we can make this interval become a true. We've got a true expression, which means now we've got or true or true and true and true or whatever. It means the whole expression can be made true. Else if left false count at start is equal to 0, exactly equal to 0, and right false count at end is exactly equal to 0, then we've succeeded. Finally, if there are no all true intervals to the outside and the interval we're in has a false to the left or the false to the right, it cannot be made true, which means we can't do it. End. Let's go ahead and put an end line on the end, just to make it a little bit slower. I recently learned that end lines are actually much slower than \ends. I'm not going to mess with that optimization just because I'm used to typing end line. But as it turns out, the \ends are much faster. Okay, let's go ahead and clear, make logical. Let's go ahead and run this and just see if it generally makes sense. Paste, whoop. Oh, I gotta run it first. I gotta run the code for the code to run. Logical. That should have been an N. All right, we gotta debug this. Let's start. Uncomment this. I already know this is gonna be something stupid. We'll find out in a minute here. I have no goal.
A few moments later.
Oh, I didn't read the goal in. Okay, cn goal. I knew it was gonna be something stupid. Make logical pasta. Yep, and I got my N. Okay, let me clean out. We'll just pretend that never happened. I'll probably leave it in the final video just to show a little bit of my debugging process. I don't want you all thinking I'm perfect or anything. All right, so 3 to 9, impossible to make false, and that makes sense because I got an or true or right here. 3 to 9 true is gonna be true no matter what you do. 3 to 11, it should be possible to make this false because if you replace this with false, I've got true and false or false and false. So that's good. It should also be possible to make it true because if I make that true, then I've got true and true or false and false. This looks like this is pretty good. Let's go ahead and submit this and see if it goes through. Oop, gotta log in. C++, choose file, logical CPP, submit. It's a lot of test cases. Again, the core to this one is, as soon as you see that n is 2 times 10 to the 5th, and q is also 2 times 10 to the 5th, you can't skip queries. It means we can't do it with a linear search. This is a hard thing to do at the bronze level. As long as you realize that there's no way to make queries shorter, and we can't do 2 times 10 to the 5th times 2 times 10 to the 5th, because that's too big, we have to figure out how to make this shorter. It means you had to come up with something in constant time. As soon as you have to come up with something in constant time, first thing you should do is run through and think, can I do this with something like a prefix sum or something where you're counting the difference between here and here? Okay, that's it for C++. Move on to Java. Import Java util scanner class logical. We're gonna have to create the scanner. Scanner sc equals new scanner system in. Int n equals sc next int q equals sc next int sc dot next line. We're going to set up our mini arrays. Char expression equals new char n plus 1 int left true int equals new int n plus 1 int left false count equals new int n plus 1 int right true int equals new int n plus 1 int right false count equals new int n plus 1. Okay, we do for int I equals 1, well I is less than equal to n, I plus plus. So we're going to do string temp equals sc dot next, and then I just need to make sure I do an sc next line at the end. I'm going to do expression at I equals temp char at 0. In C++, I have to initialize all these to zeros. You can see I'm doing all that here, setting them equal to 0. Java will do it all for me, so I can just assume these are all full of zeros. My next step is to do my left to right pass. So we're going to do int false count equals 0 and int true intervals equals 0. I'm going to do my left to right pass first. Int I equals 1, well I is less than or equal to n, I plus plus. If my expression at I is equal to the letter f, my false count goes up. Else if my expression at I is equal to an or, if my false count is 0 within that expression, I've hit no falses. If I've hit no falses, my number of true intervals has gone up. True intervals plus plus. And every time I iterate, my left true interval at I needs to be set equal to my true intervals. My left false count at I needs to be set to my false count. I want to know what's to the left of it, not including it. Because if I'm cutting something, I can't change whatever's to the left of it. So if I hit a false, that doesn't cause me trouble until the next item. If I hit the false, and I'm cutting at that false, there's no falses to the left of it, then I'm fine, and I can cut that false out. The right to left pass is exactly the same. We're just gonna copy paste this. I'm just gonna make a couple little modifications. So I gotta take these ints out, so I don't redeclare these variables. I'm gonna start at n and go down to 1, and then all these where it says left needs to become right, and then right false count. This is a good time for a sanity check. I'm going to make a real quick for loop. I equals 1, well I is less than or equal to n, I plus plus. We're gonna do system out print line. I wanna know the value of I. The expression at I. What is my left true intervals? Little C++ sneaking in there. Java. Okay, left false count, right false count, my right true interval at I think that's everything. Let's real quick compile that. False count, it's the full word false count. Java, logical. I can grab this. I'm going to grab this from C++. This was the test case that I had in the visualization if you watched that. So we're just going to go ahead and feed that in. Ooh. Oh, because I'm not doing the queries yet. Okay, I got to feed that in without the queries because I haven't written the query part yet. Ooh. Oh, I missed something. When you hit an OR, whether or not it's a true interval, false count has to be reset back to 0 because that means that you're on a new subset. And no matter what the false count was, you're starting back over for this new interval. That's also going to be the case back here. Java C, Java logical. Let's recopy this. Okay, that looks a lot cleaner. But we're just going to look at the left first because we're going to do the right on the second pass. First pass, I have true and true. Or, and then remember this or right here is where if the false count is 0, true intervals is going to go up. But we're not going to see that recorded until it loops around. So then as of this false, there is one entire interval to the left of that false where everything is true. And that's that true and true. False and notice here, then my false counter has gone up to 1 for the first time because I hit a false. False and, which means that from here, if this is the left side of a cut, then this subinterval right here to here, between that or and that or, there's a false to the left of this. So if I'm cutting from here to the right, I can't change this false. In this particular case, it won't matter because there's a true and true here. Here's a false or, doesn't really change anything. There's a false to the left of it, but that's not part of an expression. So that's never going to get read because you're never going to cut starting or ending from an or. It's always cutting from a true false to a true false. Here's a true or true. And then when I hit that or, my counter goes up to 2. Now, it turns out that the exact count doesn't really matter. I really could just do this with trues and falses. I liked the counter because then it kind of lets me see if there's anything breaking down exactly where and how it's breaking down. Integers take up a little bit more space than Booleans do, but it's not really a huge difference in this case. And being able to see the count helps with debugging. Here by false and then my false counter goes up to 1 and false. So the left to right looks like it worked. Now we'll go right to left. False and, now my false counter went up to 1. You can see that. False or false counter went up to 2. But again, we can't cut it an or, so the actual value there doesn't matter. True or, and that's the point at which my true interval counter goes up to 1. So here's true interval counter now at 1. And that'll be 1 all the way down. You notice this very last one goes true and true, but there's nothing to the left of it. So the fact that it has true and true, I can't raise the counter of the number of things to the right of it that are all true because there's nothing to the left of it for that to show up. But if there was something to the left of this, then that would go up to 2. Now the significance of this is if I'm cutting, if I have, this is my interval, I put the interval counters on the outside. If from here, for example, if I cut starting from 5 to anywhere, I can only make that true no matter what, because this 1 tells me that to the left, there's an all true interval. Likewise, if I'm ending a cut at 9, no matter where I'm cutting from, at 9, that shows that there is an all true interval to the right of that, and that's this or true or right here. The only way to ever make this false is to cut from something that has a 0, and you can only cut from an odd number, which would be here. If I cut this interval, then it's possible to make this false. It's also possible in this case to make it true. The reason why it's possible to make this true, because in this case, this interval has no falses to the left of it. I'm pretty happy with this output. That's what I was expecting to see, so we'll comment this out. And now we'll write the logic for the queries. For int I equals 0, I less than q, I plus plus. We have int start equals sc next int end equals sc next int, string goal sc next, and then we'll just do sc next line. If goal char at 0 is a false, then I'm going to try and make the subsection a false. Otherwise, if it's not a false, it must be a true. The goal is what I want it to be. If I want it to be a false, then if the left true interval from start is greater than 0, that means to the left of the starting point, there's an interval where everything is true. If that's the case, or right true interval count at end is greater than 0, then there's no way to make the expression false because we've got a all true expression that's outside of our range of influence. If that's the case, we can system out print n because we can't make it false. If it's not the case and we're trying to make it false, if I have no all true intervals to my left and no all true intervals to the right, and I'm working on an interval, if I make some part of that interval false, the whole interval's false, which means we've solved it. So system out print y. And that's it for it. The true is a little trickier. If we're trying to make it true, then if left true interval at start is greater than 0, or right true interval end is greater than 0, then it's true anyway. So sure, we can make it true. Print y. Here's where it gets a little trickier. Else, if the number of falses in the subsection I'm in, left false count at start is 0, and right false count at end is 0, then what that means is that I'm within an expression, or perhaps straddling multiple expressions, but either way, I'm going to turn this into a single expression. There's going to be an or, there's going to be maybe some stuff to the left, the part that I'm cutting, maybe some stuff to the right, and an or. And again, there might be multiple expressions in here, it doesn't matter. All I know is that from the starting point, there's no falses outside. From the ending point, there's no falses outside. I've selected a subsection where every single thing outside of it is a true. And if that's the case, then I can make this part true, and this whole expression becomes true. So if that's the case, system out print y again. However, if there are either falses outside of the expression on this side or falses outside the expression on this side, and none of the expressions on the outside are all true, that means I have no true expressions out here, I have no true expressions out here, and I'm cutting a subsection that contains falses that are outside of my range, which means the expression that I'm in is going to be false, which means everything's going to be false, which means I can't make it true. System out print, not possible. Finally, we're going to do a system out print line. Java C, logical.java. Oop, is that not what I named it? Oh, left false CT. And then let's throw this in. Okay, first one is from 3 to 9. From 3 to 9, if my goal is to make it false, I can't do it because there's an or true or here, which means it's true no matter what. But if my goal is to make it true, I can do it because there's already a true. And so that's the no and the yes. Next is from 3 to 11. If I want to turn this to false, there are no all true intervals outside here because this is the middle of an interval. And even though this straddles several ors, I hit to here, there's no all trues to the right of the interval, and there's no all trues to my left. I can just make this part false, and I'll have true and false, or false and false. So it is possible to make it false. But it's also possible to make it true because the number of falses within this interval to my left is 0. Now, if this was a false here, then I would have absolutely no way to make this true because now I'm cutting from here to here. My count of falses is greater than 0. And if my count of falses is greater than 0, then even if I make this true, I've got a false within the expression and I have none on the outside. This looks like this is working correctly, so I'm just going to go ahead and submit it. All right, looks like we breezed right through that one. All right, let's move on to the Python. 3. I'm going to do enq equals map int onto input dot strip dot split. And what's going to happen here is my input, it's actually 15.4 in new line. When I do strip, it'll take off the new line. When I do split, it'll turn it into a list of strings. And when I map int onto that, it basically is going to call the int function on each one of these individually and replace it. So the string 15 will get replaced by the integer 15. Likewise with the 4. And then when I set enq equal to that, it'll unpack them individually. N will be 15, Q will be 4. Expression, input. I want to do strip and split on that as well. Split expression equals. And I could do this with list comprehension. Not everybody at the beginner level knows how to do it, and I don't want to force that on people. List comprehension is significantly faster, but it won't make a difference on your ability to pass USACO. And because it's not strictly necessary, I'm going to leave it out of these tutorial videos. They're going to be like G0 for G in expression. This is the list comprehension solution. Basically, for everything in the expression, I want the first letter of the thing. We're going to keep it simple. Just do expression for item in expression, append exp0. I'll just keep it easier to read. With that, I need left true intervals to be a list of zeros times n plus 1, so I can one index it. And left false count, 0 times n plus 1. Actually, the expression is going to have to do that as well. We'll go ahead and put an X at the beginning. Same thing with right true interval, count. Okay, I think that's good for setups. We will now do the left to right pass for I in range 1 to n plus 1. False count equals 0. True intervals equals 0. For every index, left true interval at I is going to be equal to true interval, and left false count at I is going to be equal to false count. If the expression at I is a false, I have to raise my false count by 1. False count plus 1. Elif expression at I is an OR, I've hit an OR, which means I've hit the end of an expression. If I counted no falses from the last OR to this OR, then that means that my number of true intervals has gone up by 1. If false count is 0, then true interval plus 1. And then either way, my false count needs to go back to 0 because I'm now on a new interval. And then when I loop back around, I'm not recording this until I loop back around, because if I hit a false, that doesn't mean that there are falses to the left of it. It means that there are falses to the left of whatever's to the right of it. So my false count goes up, I loop back around, and now I can start recording that there was a false, which means this expression is going to be false no matter what I do because I can't cut that false out of it. I think that's it for that. For I in range n to 0 going in the negative direction. These are a little confusing for me. In the C++ and Java, I can control it with less than or less than equal to. In the Python, it's always less than, never less than equal to. This is essentially the exact same thing, but I do have to remember to set false count and true count back to 0. This is all going to be the same, except this is right, and otherwise everything's the same. I'm going to do a real quick sanity check. We're going to do for I in range 1 to n plus 1. I want to print out I, the expression at I, my left true interval at I, a false count I, right true interval at I, right false count at I. Whoop. And we're going to test this example input that I had from the visualization here. Python 3, logical pasta. Oh, right, I didn't do the queries yet, but let's see what we have up to the queries. So I got 15.4, true and true or true, et cetera, et cetera, et cetera. Oh, they're all zeros. Everything's a 0. Have I messed up the expression? Print. Oops, actually go to where a line of code can go. Print. Oh, there should be item 0. This should be item 0. It's good to do little tests when you do your input. Sometimes I skip them. Just real quick, what I did there is I did expression 0, which was the first part of the expression, which is this true, and I just appended that 15 times instead of appending the first letter of every individual item. There we go. So true and true, or false and true, et cetera, et cetera, et cetera. So we're just going to run through this. In the beginning, my first one is how many entire true intervals I have to the left of that particular location. My second one is how many falses I have to the left of it within that same expression. So I've got true and true, or, and then when I hit that or, that's the point at which if my false count, which is the second number, is 0, my true interval goes up by 1. But that doesn't record until I get to this next one, because I'll never cut to or from an or, but once I hit this false, if I cut from this false, this 1 here indicates that I've got an entire expression to the left of this, which is this true and true, which everything is true, which means that if I'm cutting from here to something later, I can't make a false, and I have to make a true, because true and true is already going to make the whole expression true. False and there's my false count up to 1, true, which means that if I were to cut from this true, I can't turn this expression to a true because there's already a false to the left of it within that same expression. If I have false and anything, I can't turn the expression true because I can't do anything about the false. Or, and we set our false count back to 0, but notice our true counter is still 1 because there still is an all true interval to the left of this. True. Or, here's the second expression where I have no falses, which is going to bring my expression count up to 2. Technically, the fact that this is 2 doesn't matter at all. Really could just do trues or falses. I would like to have counters in because then I can see exactly what the count is. Then if I'm getting something that's incorrect, I'll see where the incorrectness happened. The Booleans might be a little bit quicker, but it doesn't really make a huge difference, and it's the same time complexity. And it's a little easier to debug and see what's going on. There might be a version where there's parentheses or something where it would make a difference, but in this case it didn't matter. So I have false and then there's my false counter going up to 1. Second false, if there's anything past that, my false counter would be up to 2. Now we're going right to left. My first one is how many all true intervals I have to the right. My second one is how many falses I have to the right. So I have false and so that 1 indicates there's a false to my right. Second false, or, which brought my counter up to 2. New interval, true, or marks the end of a interval. False count is 0, which means now my true interval counter is going to go up to 1, and that's where that 1 is coming from. False, or, true, and false, or, false counter made up to 1, but again, that's not going to make any difference. True and true. Now you notice that the true and true counter, that didn't get up to 2 because there's nothing to the left of this. This true and true is not to the right of anything, so it's not contributing with my to the right count. If I cut from 5 to, for example, 5 to 9, shows that there's an all true to the left of that, which means if I cut from here to somewhere, no matter where I cut to, it's going to be true no matter what. Likewise, ending here at this false, there's an or true or to the right of this. So if I end my cut anywhere here to here, it's true no matter what. Unless I cut from somewhere that has a 0, and I can't cut from an or, so I'd have to cut from this true. If I cut from here, where there are no complete all true intervals to the left of me, and I cut from here ending at this location, which is that or true or, where there's no all true to the right of me, this is going to be the only subsection where I can actually make a false, because I have no all true intervals to the left, I have no all true intervals to the right, which means if I make this interval a false, then there's no true intervals anywhere. If I make it a true, then I can make it so that there is an all true interval. And we'll look at that in a second when I actually do the queries. This is doing what I expect it to do, so we'll comment that out. Just comment that out. For I in range Q, start, end, goal equals input dot split, start equals int start, end equals int end. If my goal is to make it false, I can't have any all true intervals to my left, and I can't have any all true intervals to my right. If my left true interval at my starting location is greater than 0, or my right true interval at my starting location is greater than 0, then it can't be done. No, with end being nothing. When I say end equals that, it means I don't want it to end with a automatic new line. I want to end it with nothing. If I put a comma here, then it would end it with a comma space. Else, if there are 0 to my left and 0 to my right, I can make this false, and then I've succeeded. Print y, end quotes. Otherwise, if my goal is not false, my goal must be true. If my goal is true, it's a little trickier. I have 3 things to check for instead of 2. First one is if left true interval at start is greater than 0, or right true interval at start or end. Ooh, just caught that. That should be end. If there are true intervals outside of my range and I want to make it true, I've already succeeded. Elif, I want to try and make this interval true, but there are falses within this sub-expression outside of my range. That false can't be made true, which means I can't make it true. If my left false count at start is equal to 0, and my right false count at end is equal to 0, if they're both 0, then that means that I'm in an interval that has no falses outside of my range. So if that's the case, then yes, it can succeed. And finally, so I don't have any all trues, and then within the expression I'm in, I've got falses I can't do anything about, which means I can't turn it true. Okay, and then I think that's it. And we'll just go ahead and print it at the end. We'll go ahead and check the queries. These queries, I think I made them to handle most general cases. Python 3 logical, pasta. So 3 to 9 is from here to here. I have a or true on my right side. My right side shows a 1 counter here, which is that or true or, which means I can only make it true. So my goal is to make it false, I can't do it. If my goal is to make it true, I can do it. From here, if I cut from 3 to 11, you notice that even though I've got or, false and true, or, false and true, or, in this expression, to the right of me is or, false, and false. So I have no all true expressions to my right. And then within the expression I'm in, I have a true and. Because there's no falses to the left of this, if I want to make this a false, the whole expression becomes false because I've had true and false, or false and false. And if I make this true, because I have no falses to my left, the whole thing can be true, because then I'd have true and true. Now, if this first one was a false and I was cutting that same range, then I can't make it true, because I don't have any all trues to my right, I don't have any complete all trues to my left, and the expression I'm cutting would have a false to the left of it, which means whether or not I make this true, from here to here, I can't do anything about the false. All this output looks about like I would expect it to, so we're gonna go ahead and submit this and see if this works. Logical PY, submit. All right, and that's all clear. And that's the Python version. Essentially with these interval problems, it's really important to have good bookkeeping. The big giveaway on this one is knowing that the number of queries here could be 10 to the 5th. We can't reduce the number of queries. And since we can't do 10 to the 5th squared, we have to find a way to make this simpler, which means either it's got to be logarithmic time, which means a binary search, which doesn't do us any good because there's no way to alphabetize or order or sort these. And with the remaining interval, we have to have it in constant time. And if we have to have it in constant time, that means an array with the same length as whatever the query length is, or potentially multiple arrays or lists where we're recording what we've seen so that when we have a starting point and an ending point, we can look at this one to see everything that's to the left of me, which is outside of my control, or everything to the right of me, depending on the problem. And from the ending point, again, recording everything inside and outside. In this particular problem, since I was cutting an interval, I have control over what's this, which means I don't have control over what's there. So if I can control this, then all I need to know is what's outside of that interval, what's outside of that interval. There's another one that's kind of similar to this that has to do with lifeguards. I think that's a silver problem where you're counting how many cows are working at any given moment. So you can figure out at the end, like which cow to fire based on which cow has the least amount of time they're working alone. I'll probably do that one next. I like the lifeguard problem a lot, but that's a silver problem. So that's a problem. Hopefully this was helpful, and I'll talk to you in the next one.